All right, welcome to lesson 1 of module 3. And in this module, we're going to start dealing with graphs, what we can represent with graphs, how do we graph, what are the different types, that kind of thing. Okay, so we're just going to get right into it. And we are going to start by looking at this particular situation. It says that the distance a delivery van is from the warehouse varies throughout the day. The graph shows the distance from the warehouse for a day from 8 a.m. to 5 p.m. So on the x-axis, we have time in hours. On the y-axis, we have distance away from the warehouse in miles. And it asks, it says segment 1 shows that the delivery van moved away from the warehouse. Okay, what does segment 2 show? Well, segment 2 is right here. It also shows that the van is continuing to move away from the warehouse, but this segment is not as steep, so the van must not be moving as quickly, meaning it's covering less distance as time goes by in segment 2. All right, so I said the segment, meaning segment number 2, is not as steep, so the van is still moving away from the warehouse, but it's not moving as fast as segment number 1. Okay. Based on the time frame, what change in distance from the warehouse is represented by segment 6? Okay, well, let's get to segment 6 in a minute. Let's just go from segment to segment. 1, the van is moving away fairly quickly. 2, the van is moving away not quite so quickly. 3, segment 3 is horizontal, which means there is no change in distance as time goes by, which means that for this van, the van must be stopped. Maybe he has put his van in park and he's offloading some things that he's delivering. Then segment 4 is steep again, so he's moving away from the warehouse fairly quickly. Number 5 is another horizontal segment, so that must mean that the van is stopped again. Number 6, you have a slope that's in the opposite direction of these upward slopes. So this is sloping downward. Remember, your distance is miles away from the warehouse. So he must be moving, but this time he's decreasing his distance away from the warehouse. So he must be on, like the latter half of his route, and he's coming back towards the warehouse. Number 7 is another horizontal. He makes another stop. 8 is slow. Maybe he's in traffic. 9, a little faster, maybe he gets out of the worst of the traffic and he gets back to the warehouse. Okay. All right, based on the time frame, what change in the distance from the warehouse is represented by segment 6? That's when he starts to come back toward the warehouse. All right, so for B, I said the delivery van begins to drive toward the warehouse. That's the first segment where the slope is decreasing. C, which segments show intervals where the distance did not change? Those were your intervals where the van seemed to be stopped. Those are your horizontal segments. That was 3, 5, and 7. What is a possible explanation for these segments? Well, I'm not going to write that down because we basically talked our way through it. Left the warehouse quickly, still driving away from the warehouse but slowly, makes a stop, drives fast, makes another stop, drives fairly quickly but back towards the warehouse, makes another stop, drives quickly but not as quickly as like 4, and then number 9 drives even quicker than number 8 and back towards the warehouse. All right, join me on page 98. It says graphs can often be drawn to represent real-life situations. These graphs are not always easily derived from equations, but rather represent certain situations. For example, these graphs may include the amount of rain over a certain period of time or the height of a bouncing ball, etc. Okay, so we're just going to hop right into the example. It says 3 hoses fill 3 different water barrels. A green hose fills a water barrel at a constant rate. Okay. A black hose is slowly opened when filling the barrel. So like you're slowly opening the hose to allow more and more water to flow into it. A blue hose is completely open at the beginning, so you've turned it all the way on, and then it's slowly closed as time goes by, and the three graphs of the situation are shown below. Okay, first of all, hang on, let me find a green pen. Green pen for a green hose. Hopefully you've noticed that the green hose filled at a constant rate. A constant rate on a graph is going to look like a straight line. So this one should be the green hose. A black hose is slowly opened when filling the barrel. So at the beginning, the black hose is not open very much, and towards the end, it is, which means that it's going to fill slowly at first and then more quickly. So this is the black hose. Down here, it's filling slowly because the hose is mostly closed right now. But later on, it's filling quickly because the hose has been opened up. Right? And then C has to be the blue one. It's completely open at first, so on the blue one it fills very quickly at first and then slowly towards the end. Okay, let's look at the questions down at the bottom. Which graph best represents the amount of water in the barrel filled by the green hose? We've already said it's B. Since the flow of the water is constant, the amount of water in the barrel should be a steady increase. Example B, 1B, says describe the water level represented by each graph, then determine which graph represents each situation. Okay, and I've got a little bit of cheater notes because I've already filled them out, so here we go, because we've already discussed this, so let's just get the writing done. Okay. All right, so describe the water level for A. Water level fills slowly, then the water level rises rapidly after the hose is opened. We've already talked about that. For C, water fills quickly at first, then more slowly when the hose is closed. Graph A is the black hose. Graph C is the blue hose. And could a graph of the amount of water in a water barrel slant downward from left to right? Yes, it could. They're asking, could you have like this situation? And yes, you can have that situation if you're draining the water instead of filling the water barrel. Okay, let's go to the next page, which is page 99. All right, you and a friend are playing catch. You throw 3 different balls to your friend. You throw the first ball in an arc and your friend catches it. You throw the second ball in an arc, but this time the ball gets stuck in a tree. You throw the third ball directly at your friend, but it lands in front of your friend and rolls the rest of the way on the ground. And you have 3 graphs of these situations. Okay? So figure out which one you think should be A, B, and C. All right. So on each graph, I'm going to say that this is about the height that you would release a ball, you know, because it's not, you're throwing it, obviously, so it's not absolutely on the ground. This one, you throw it directly at your friend and it rolls on the ground. This one, you threw it up and the friend caught it. This one, you threw it up and it got stuck in a tree. Okay? So which graph represents the situation where the ball gets stuck in the tree? That is graph C. Describe the height of the ball represented by the other 2 graphs. Okay. Again, this is kind of arm height. So B height is arm height, then it goes up in an arc, and then it's caught again by somebody's arm, so it's kind of caught at arm height, maybe 3 or so feet off the ground. A, ball starts at arm height, but then ends at a height of 0 because remember, it's rolling along the ground. Okay? So even though they didn't put numbers on these graphs, hopefully the shape of the graph helps you to represent the situation they're describing. All right, and then we're going to move down to example 2, and it says, sketch a graph of the situation, tell whether the graph is continuous or discrete, and determine the domain and range. Okay, well, we really haven't talked about domain and range yet. We will do that. But go ahead and highlight what I highlight. Okay, some graphs that represent real-world situations are drawn without any interruptions. In other words, they are continuous graphs. A continuous graph is a graph that's made up of connected lines or curves. Other types of graphs are not continuous. They are made up of distinct, unconnected points, and these graphs are called discrete graphs. You will understand a little bit better what I'm talking about when we start looking at more of these graphs. Okay, I'm going to remind you, because for some reason they haven't bothered to tell you or remind you yet what domain and range is, although I think you've done domain and range. Domain is your set of input values, basically your x values. Range is your y values or your output values. Okay? A student is taking a test. There are 10 problems on the test. For each problem the student answers correctly, the student receives 10 points. The grade is made up of multiple unconnected points, so the graph is discrete. Why? Because you're either going to miss 0 or 1 or 2 or 3 or 4. You're not going to miss like 0.25 or 7/8 of a question or whatever. Okay? I mean, I know sometimes I give you guys partial credit, but let's just say the questions are either right or wrong. So we're not going to draw a continuous line, because your grade is either going to be derived from missing no problems, or missing 1, or missing 2, or missing 3, and not stuff in between. Okay? So this time, for this situation, we don't connect the points, and we call this a discrete graph, because the areas between the points don't really make sense for this situation. All right, I'm now on page 100, and let's look at this situation. B says a bathtub is being filled with water. After 10 minutes, there are 75 quarts of water in the tub. Then someone accidentally pulls the drain plug while the water is still running, and the tub begins to empty. The tub loses 15 quarts in 5 minutes, and then somebody plugs the drain and the tub fills for 6 more minutes, gaining another 45 quarts of water. After a 15-minute bath, the person gets out and pulls the drain plug, and it takes 10 minutes for the tub to drain. Okay, I am hoping that you guys will understand that since the tub is gradually, continually filling with water, that this situation is a continuous graph, meaning we're not going to have individual points like we had on the test grade one. Okay, this one we're going to connect and draw lines. The domain, remember, is your set of input values or your x values. So your x's are your times, and the range is your level of water. Okay, so let's see what we get when we put all of that together for B. Okay, so it makes sense that this graph is a continuous graph. The domain I got from reading the problem, because 46 minutes go by in total for this whole situation. And the range, my set of y or output values, is from 0 to 105 quarts, because I can get as high as 105 quarts with all of the things that happened. Okay? And then, because I tend to color code everything, the lime green is the initial situation. The dark green is when they pulled the drain for a few minutes. The kind of hot pink is it filled for 6 more minutes, gaining another 45 quarts. Then the blue is somebody took a bath. Something happened to my paper. And then the orange is that they pulled the drain and they let it empty. Okay? So there's what your graph should look like. But again, it's not dots, it's a continuous line, because the amount of water in the bathtub can change very gradually, and we need to represent that as a continuous graph. Okay? All right, let's look at this situation down here where it says your turn. So we're still doing things together even though it says your turn. And I'm going to finish this one up with a super quick screencast because I'm about out of time on this one.